Hi folks, welcome to our YouTube channel. This week I'm going to be interviewing Dr. Stephen Hannon about a recent paper that you just finished up. Star cluster classification using deep transfer learning with PHANGS-HST. To begin with, maybe you could just give us some background on star clusters, what's exciting about them, why we're interested in them.
Yeah, so for me personally, the first science projects I worked on in getting my PhD was looking at the clearing timescales of star clusters. So basically how quickly stars will disperse the gas from which they were born. And in defining timescales for this clearing, we needed to know the properties of the star clusters themselves, how old they were, how massive they were, etc. In these studies, we use thousands and thousands of star clusters, so we have as many different data points as possible.
So in this paper, you're working to classify this huge catalog of star clusters, right? And you're sorting them into different categories. So what's the difference between these categories, and do they correspond to physical differences, or is it just kind of an observational?
We have 4 different classifications of star clusters that we use. Typically, this is done by a human. So our expert for the PHANGS collaboration is Brad Whitmore. And basically, he goes through thousands of candidate clusters, which are determined through magnitude, concentration index. And for each of those objects, he'll classify it as one of these 4 classes. The class 1 objects are going to be symmetric and compact with a single peak. Typically, these are indicative of older star clusters. Take time generally to gain that symmetry. And then we have class 2 clusters, which are going to be still compact but slightly asymmetric. And then class 3, which are sometimes included as star clusters. Sometimes they are excluded from star cluster studies because it could still be just chance superpositions, but they're basically a compact association of stars is what we'll also refer to them as. We define those as having at least 4 stars within a 5-pixel radius. But as you can see in this image, rather than having a single peak like class 1 and class 2, we have multiple peaks. And then our final class is a non-cluster.
So that, I mean, 21,000 candidates, it's a lot to work through, and with the size of the PHANGS survey, we're looking forward to even more, right? So that was what kind of pushed you to look to machine learning to start categorizing these?
Yeah, absolutely. For the entire PHANGS-HST survey, we have a total of 200,000-ish candidate star clusters. And so rather than have Brad dedicate 10 times as much time as he already had, we wanted to go ahead and see what we could do with machine learning in order to kind of take over that classification. And then that having these machine learning models to classify allowed us to test how well they could do for fainter objects, for example.
But what's kind of the agreement, or how did the machine learning approaches do compared to people for PHANGS?
Yeah, so generally speaking, they are very comparable, which is essentially the best we could hope for. Because if a human is only able to reproduce it 70% of the time, and the data we're feeding it is that human-based data, then as long as we're comparable, that's the best we can do.
Personally, I've never worked with machine learning, so I know there's different implementations or algorithms, and how did you go into that?
Yeah, so I was also on a machine learning star classification project with Legis, and in that one, we had collaborated with some people over at University of Illinois, Urbana-Champaign. And so this was a merging of computer science and astronomy here, and we essentially followed their lead. They had chosen to look at deep transfer learning. And basically what that is you take these models which have been trained on huge data sets of images. It's called ImageNet. It has millions of images, and basically the initial layers of the models train on general features of any image. So it could be, specifically of dogs, cats, trees, automobiles.
Not specific to star clusters.
Not yet.
Okay.
So basically training on this wide variety of images from ImageNet allows the models to learn general features such as edges, shapes, boundaries, etc. And then we take the last layer of those models and remove them. And then that's where we plug in our data, essentially, which tailors the models to whatever specific objects you are trying to classify. So that's what led us to using the ResNet models by Hay et al. That remains one of the most prominent papers in computer science and machine learning, and then also the VGG models by Simoyan et al. And so the models I used for my paper are the same models that we decided to use for the Legos-based machine learning models.
So you mentioned the Legos set, which kind of came before, and you did some comparison of the Legos models with the PHANGS models that you worked on here.
Mm-hmm.
What's the difference between those two data sets and what we're working from there?
Yeah, so the primary differences between the two, are that the Legos sample comprises a different set of distances for all of its galaxies. Generally, they're between like 3 and 10 megaparsecs, whereas the PHANGS sample lies more in the 6 to 20 megaparsec range. And then secondly, the class 3 definition actually was more specified in the PHANGS sample, as I said earlier, 4 stars within a 5 pixel radius, rather than kind of just generally being multi-peaked. Mm-hmm. This is also one of the figures that's in the paper, where we actually use the models that was trained on the Legos data to classify PHANGS objects. And that is this plot on the right. This is a confusion matrix, basically showing the accuracy of the model. And the one-to-one accuracies, that is, if the model classifies it as a 1 correctly, or the model classifies it as a 2, 3, 4 in agreement with the human, that is going to be the diagonal here. So this is showing that the Legos models classified human-classified PHANGS objects, class 1, 61% of the time, and then only 27% of PHANGS class 2 objects were correctly classified by the Legos models, 26% class 3, and then that shoots up to 83%. So another way that you can look at this plot is that many of the PHANGS class 1, 2, and 3 objects, as classified by Brad, were essentially thrown out by the Legos models as class 4s or artifacts.
Yeah, so can you show us what PHANGS can do?
Yeah, absolutely. So instead, we made our own models, again, based on 21,000 objects that Brad had classified. And these are our results right here. And generally, we're seeing, again, between 60 and close to 80% accuracy for our models. So our models are classifying PHANGS objects a lot better than the Legos models were. But we actually do then use our PHANGS models to classify Legos objects, and actually find that in doing that, our models are more accurate than vice versa, than when the Legos models are classifying PHANGS objects.
So we're looking at many different galaxies, many different regions. Do you see that your models are able to classify certain galaxies much better, or what kind of trends did you find with properties of galaxies?
Yeah, so there were a number of properties that we did look at. Again, one of the main differences between the Legos dataset and the PHANGS dataset are the galactic distances involved. So that was the first thing we were going to look at. And here We can look at the overall accuracy of the models, that is just averaging the class 1, 2, 3, 4 accuracies together and plotting them versus distance. And while there's not a significant trend, you can see at least there is a slight downward trend. That is, accuracy tends to decrease with increasing distance.
Cool. So you looked at this kind of distance trend. You found it's harder to classify further sources. Kind of makes sense. Were there other trends that you also?
Yeah. So one of the interesting trends we found was actually with the color of these objects. And for class 1 objects in particular, if you recall, I mentioned earlier, class 1 objects tend to be older. And as shown in this color plot, the median is denoted by the larger red circle. And you can see that median color is somewhere, pushing near the 1 gig a year point in the stellar population model. And so, again, many of these class 1 objects are generally older. And so if you have a symmetric object, which is in fact younger, we actually found that those were classified worse by the models, or the models were less accurate in classifying younger class 1 objects. Those younger objects are going to be located in the same color space as where the class 2s and 3s reside. So it could be some confusion with the color there that is presenting these models some difficulty. So we do see that the median color for these class 1 objects is generally older, whereas the median color for the class 2 and 3 objects are generally younger. And the accuracy of the models is actually reflected in the SED ages of these objects also. That is, so as class 1 objects get older, the models actually improve their accuracy. And then conversely, as class 3 objects get older, the model accuracy decreases because there are going to be a lot fewer older class 3 objects, so it could then be conflating them with potentially class 1 objects.
Cool. So you've generated these models. They're now ready to go on any more data that comes in, or the other galaxies that we didn't look at. What are the next steps, and where would you take this?
Yeah, absolutely. So the PHANGS-HST program has 38 total galaxies. These models were trained on the first 20-ish that were classified. And so I mentioned earlier, but across all 38 galaxies, we have about 200,000 cluster candidates. And these models have been used to provide machine learning classifications for every single one of those candidates. And those catalogs will be publicly released. And we have Daniel Mashman working on, or leading that paper for the cluster catalogs.
That's exciting. Would these models be specific to PHANGS, or could anyone use these on different data or on their own projects?
Yeah, so you can use these models for star clusters anywhere theoretically. I'd love to see them implemented wherever. I actually do also have a Jupyter notebook that is also publicly available that basically walks you through the process of generating your images for all of your star clusters, all the way through providing classifications for your set of objects.
Big thanks to Stephen for the interview. You can check out a link to that Jupyter notebook as well as his paper and other cool PHANGS projects in the description box below. Thanks for watching.